Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Applications of Operational Amplifiers under the paper Measurements and Instrumentation. So students, let us see what we are going to learn in this module. In this module, the various applications of operational amplifiers are studied. Operational amplifier as adder or summing amplifier is studied in the inverting and non-inverting configurations. The expressions for output is derived. The working of op-amp as subtractor is studied. Op-amp is studied as differentiator. The practical circuit of differentiator is also discussed and the frequency response is studied in detail. Operation of integration using an op-amp is explained along with the practical circuit and the frequency response. Finally, application of op-amp as non-inverting comparator and zero crossing detector is also demonstrated. Operational amplifiers form the basic building block of various linear and nonlinear analog systems. The basics of op-amp, along with its working in the inverting and non-inverting configuration, has already been discussed in the previous module. In this module, we will discuss the applications of op-amp. Op-amps are used in various applications such as adder, subtractor, differentiator, integrator, comparator, zero crossing detector, etc., which are discussed. Let us begin with the adder or summing amplifier. Adder is one of the most useful op-amp circuits used in analog computers. This circuit is used to add AC as well as DC signals. These are categorized as inverting summing amplifier or non-inverting summing amplifier depending on whether two or more inputs are connected at the inverting or non-inverting terminals respectively. Let us first consider the inverting configuration. The circuit diagram of inverting summing amplifier having three inputs VA, VB and VC is shown in figure. We can see that the inputs VA, VB and VC are added at the inverting input. That is why it is called an inverting adder. RF is the feedback resistor. IA, IB and IC are the currents flowing through resistors RA, RB and RC respectively. IB2 is the current which is flowing in the inverting terminal and IB1 is the current which is flowing in the non-inverting terminal. A resistor R compensatory is added at the non-inverting terminal to compensate for the input bias current. Now writing the Kirchhoff's current law at node V2, we have IA plus IB plus IC is equal to IB2 plus IF. Now, using the concept of virtual ground, which is discussed in the previous module, we have V1 is equal to V2 is equal to 0, which implies that IB1 equals to IB2 equals 0. Therefore, IA plus IB plus IC is equal to IF, or I can write VA by RA plus VB by RB plus VC by RC is equal to minus V0 by RF. This can be simplified to obtain an expression for output voltage V0 to be equal to minus of within the brackets RF by RA into VA plus RF by RB into VB plus RF by RC into VC. Thus, the output voltage is proportional to or equal to the algebraic sum of two or more inputs with each multiplied by a constant gain factor. The negative sign implies that the op-amp is used in the inverting configuration. Since each input is amplified by a different factor, the circuit is called a scaling or weighted amplifier. Now consider the case if RA is equal to RB is equal to RC is equal to R. In that case, the equation for output voltage becomes V0 is equal to minus Rf upon R into within the brackets VA plus VB plus VC. This implies that the output voltage is equal to the sum of the input voltages times the gain of the circuit, which is Rf divided by R. The circuit in this condition can be used to design an averaging amplifier if the ratio of Rf and R is equal to 1 divided by the number of inputs. That is, Rf by R equals 1 divided by N. In this case, the number of inputs is 3. So, if Rf by R equals 1 by 3 or Rf equals 3 times or R equals 3 times Rf, then V0 equals to minus 1 by 3 into VA plus VB plus VC. This is the expression for averaging amplifier. If R is equal to Rf, that is, the gain of the circuit is 1, then V0 equals minus of, within the brackets, VA plus VB plus VC. That is, V0 is negative of the sum of input voltages and works as a summing amplifier. These circuits are commonly used in analog computers and audio mixers in which the number of inputs are added or mixed to produce the desired output. We next consider the non-inverting configuration. In the non-inverting configuration, 2 or more voltages to be added are applied at the non-inverting input terminal of a op-amp. The circuit diagram for a summing amplifier in non-inverting configuration is shown in the figure. As for the case of inverting amplifier, for special values of RA, RB and RC, the circuit will work as an averaging amplifier and summing amplifier. Now for values of RA equals RB equals RC equals R by 2, the voltage V1 at the non-inverting terminal can be obtained using the superposition theorem as V1 is equal to R by 2 divided by R plus R by 2 into VA plus R by 2 divided by R plus R by 2 into VB plus R by 2 divided by R plus R by 2 VC. Therefore, V1 is equal to VA by 3 plus VB by 3 plus VC by 3, which gives V1 to be equal to VA plus VB plus VC by 3. Voltage V1 is the net input voltage at the non-inverting terminal. Therefore, output voltage V0 can be written as V0 equals 1 plus Rf by R1 into V1, or V0 is equal to 1 plus Rf by R1 into VA plus VB plus VC divided by 3. Thus, it can be inferred from this equation that the output voltage V0 is equal to the average of all input voltages times the gain of the circuit, which can be adjusted by varying the values of Rf and RF. Hence, the circuit works like an averaging amplifier. It can be noted that in contrast to the inverting configuration, here no sign change or phase reversal is observed between voltages at the input and output. The circuit of the summer, which was shown in figure 2, can work like a summing amplifier if the value of gain is adjusted to be equal to the number of inputs. It can be noted from the equation for output that if the value of 1 plus Rf by R1 equals 3 or Rf equals 2 times R1, the output voltage V0 will be simply equal to the sum of all input voltages. That is, V0 equals VA plus VB plus VC. Hence, the circuit is called as a non-inverting summing amplifier. We next discuss the subtractor. Since a differential amplifier amplifies the difference between the two inputs applied to the inverting and non-inverting terminals in an op-amp. Hence, it can be used as a subtractor. The circuit of op-amp as a subtractor is shown in the figure. The input signals can be scaled to the desired values by selecting appropriate values for the external resistors. In order to establish a relation between inputs and outputs, the superposition theorem is used. Let VA equals 0 at first, and then we will calculate the output voltage due to input VB alone, that is V0B. When VA is equal to 0, the circuit is a non-inverting amplifier having a voltage divider network composed of two equal resistors having resistance R at the non-inverting terminal. Therefore, voltage at the non-inverting terminal V1 is equal to VB into R by 2R, or V1 is equal to VB by 2. Output voltage due to VB, which is V0B, is therefore given by V0B is equal to 1 plus RF by R1 into VB. Since in this circuit, RF is equal to R1 is equal to R and V1 is equal to VB by 2. Therefore, using in equation 5, we get V0B equals VB. Now let VB is equal to 0 and let us calculate the voltage at output due to voltage VA, that is inverting input alone, which is V0A. So V0A is equal to minus RF by R1 into VA. Since RF is equal to R1, therefore V0A is equal to minus VA. Therefore, net output voltage V0 is equal to the sum of V0A and V0B. So V0 is equal to VB minus VA. Hence, we get that the output voltage V0 is equal to the voltage at the non-inverting input VB minus the voltage at the inverting input VA. Hence, the circuit works like a subtractor. We now take up the next application of operational amplifier, which is differentiator. The differentiator, as the name implies, perform the mathematical operation of differentiation, which means that the output obtained from a differentiator is the derivative of the input signal. The circuit of a differentiator is shown in the figure. It may be noted that the circuit is similar to that of an inverting amplifier, except the fact that the resistance at the inverting terminal R1 is replaced by a capacitor C1 in series with input signal. The capacitor provides the low impedance part to the AC signal and does not allow the DC signal to pass through. Therefore, if a DC voltage is applied to the input, the output of the differentiator will be 0. Now, the output voltage of the differentiator can be obtained by writing Kirchhoff's current equation at node V2. Therefore, we have IC is equal to IB2 plus IF. Now, from the property of virtual ground, IB2 is equal to 0, which gives IC to be equal to IF. Let IC be the rate of change of charge, that is, IC is equal to dQ by dt. Since charge stored in a capacitor Q is equal to C1 into Vc, therefore IC is equal to d by dt of C1 Vc, which equals C1 times dVc by dt. Now the current through the feedback resistor IF is equal to V2 minus V0 by RF. Vc is equal to Vin minus V2 and V1 is equal to V2 is equal to 0. Therefore, we get Vc is equal to Vin and If is equal to minus V0 by RF. Now, using the above equations in equation 9, we have C1 times dVin by dt is equal to minus V0 by RF. Or equivalently, I can write output voltage V0 is equal to minus RF C1 into dVin by dt. Therefore, the output voltage V0 is proportional to the rate of change of input signal. where the constant of proportionality is given by minus RFC1. The negative sign in the expression of output voltage implies that the differentiated output is 180° out of phase with the input. Thus, if a sine function is applied to the input of differentiator, the output will be cosine function along with the phase reversal. The same is shown in the figure below. Similarly, a triangular input will produce a square wave output and a square input will produce alternating direction voltage spikes as shown in the figure below. The spiked output for square wave input is because of the fact that the input takes a finite time to rise from 0 to a constant value. Therefore, the output is in the form of spike. It is important to point out that the differentiator circuit, as discussed before, does not produce the expected waveforms due to certain limitations. Firstly, gain of the differentiator circuit is given by RF by XC1, which is equal to RF into 2 pi FC1. Here XC1 is the input impedance. It may be seen from the above equation that the gain of differentiator circuit increases linearly with frequency. The variation of gain of differentiator with frequency is also shown in the figure. This makes the circuit unstable. Secondly, XC1 decreases with an increase in frequency. So at higher frequencies, the circuit is highly susceptible to noise, which may cause distortion in the output. Therefore, the circuit of differentiator, which is discussed earlier, is referred to as the basic differentiator circuit. Let Fa is the frequency at which the gain is 1, or I can say 0 decibels. Then the value of Fa can be calculated by transforming the circuit into the S domain. That is, in the figure 4, Vn and V0 are now functions of S, Vn of S and V0 of S respectively, and C1 is replaced by 1 divided by SC1. Therefore, V0 of S divided by Vn of S is equal to minus Zf of S divided by Z1 of S, where Z1 of S is equal to 1 divided by SC1, Zf of S is equal to Rf, and S is equal to j omega. This implies V0 of S divided by Vn of S is equal to minus Rf C1S, which is also equal to minus Rf C1 into 2 pi Fj. The frequency F is equal to Fa corresponds to the condition when the magnitude of V0S divided by Vns is equal to 1. That is, gain is equal to 1. Therefore, RFC1 into 2 pi Fa is equal to 1, or Fa is equal to 1 by 2 pi RFC1. The problems of high frequency noise and stability can be overcome by adding two more components R1 and Cf in the circuit of differentiator as shown in figure. This circuit is referred to as a practical differentiator circuit due to its utility in practical applications. The frequency response of a practical differentiator was shown in figure 6 by a dashed line. For low frequencies, Xc1 and Xcf will be very high. Therefore, RFCF will be approximately equal to Rf, and the circuit reduces to that of a basic differentiator. Thus, the gain of the circuit increases linearly with frequency as for the basic differentiator for low frequencies. At high frequencies, Xc1 and Xcf will be low, thus C1 will behave effectively as a short circuit, and therefore Rf parallel Cf will be equal to Rf. Gain of the differentiator circuit at high frequencies is given by approximately Xcf by R1, Xcf by R1 equals 1 divided by R1 into 2 pi f Cf. This implies that the gain of the practical differentiator circuit decreases with increase in frequency at high frequencies. The frequency FB is called the gain limiting frequency, and it corresponds to the frequency at which the gain of differentiator circuit is maximum. The value of FB can be calculated by transforming the circuit of practical differentiator shown in figure 7 to the S domain as discussed earlier. Here, ZF of S is equal to RF parallel 1 by SCF, which is equal to RF divided by RF CFS plus 1, and Z1 of S is equal to R1 plus 1 by SC1, which is equal to 1 plus R1 C1S divided by C1S. Substituting these in equation 13 as described before, we have V0 of S divided by Vin of S is equal to minus RF C1S divided by RF CFS plus 1 into 1 plus R1 C1S. If RFCF is equal to R1C1, then the above equation reduces to V0 of S divided by Vin of S is equal to minus RFC1S divided by RFCFS plus 1 whole square. The frequency FB at which the gain of the practical differentiator circuit starts decreasing with frequency can be obtained by equating the denominator to 0. Therefore, RFCFS plus 1 whole square is equal to 0, which means RFCF J2 pi FB plus 1 whole square is equal to 0. Since FB cannot be negative, therefore, FB is equal to 1 by RFCF 2 pi, which is also equal to 1 by R1 C1 2 pi. Thus, addition of R1 and CF in the basic differentiator circuit reduces the problem of stability by preventing the increase in gain with frequency. Also, it significantly eliminates the effect of high frequency noise, etc. In practical circuits, the value of FB and in turn R1C1 and RFCF should be selected in such a way that FA is less than FB, which is less than FC, where FA and FB are as discussed earlier, and FC is the unity gain bandwidth of the op-amp. For proper differentiation of the input signal, the time period T should be larger than or equal to RFC1. That is, T should be greater than equal to RFC1. Differentiator circuit is basically a high-pass circuit, which is commonly used in wave-shaping circuits to detect high-frequency components in an input signal and rate of change detectors in FM modulators. Let us next discuss the integrator. An integrator is a circuit that performs the mathematical operation of integration. That is, the output signal is the integral of the corresponding input signal. The circuit of an integrator is same as that of an inverting amplifier, except the fact that the feedback resistor RF is replaced by a capacitor CF as shown in the figure. In order to derive an expression for the output voltage of an integrator, Kirchhoff's current equation is written at node V2 as I1 is equal to IB2 plus IF. Since node V2 is at virtual ground, therefore IB2 is equal to 0 and I1 is equal to IF. Current through the feedback resistor IF is equal to IC is equal to d by dt CFVC, which is equal to CF dVC by dt. Therefore, Vn minus V2 by R1 is equal to CF times d by dt of V2 minus V0. Since V2 is equal to 0, therefore we get Vn by R1 is equal to CF into d by dt of minus V0. The output voltage can be obtained by integrating the above equation with respect to time. Therefore, the integral going from 0 to t Vn by R1 dt is equal to integral going from 0 to t Vn by R1 dt will be equal to Cf times minus V0 plus V0 at time t is equal to 0. Therefore, V0 is equal to minus R1 Cf into the integral going from 0 to t V in dt plus c, where c is the constant of integration and is proportional to the value of output voltage V0 at time t is equal to 0. The above equation indicates that the output voltage is equal to the negative of the integral of the input signal with the scaling factor of minus 1 divided by R1 Cf. Thus the circuit works like an integrator. When a sinusoidal input is applied to an integrator, the output will be a cosine wave as shown in the figure. For a square wave input, the output will be a triangular wave which is shown in the figure. Here in the figure, we have assumed that R1 Cf is equal to 1 and C is equal to 0 in equation 19. Gain of the integrator circuit is given by XCF by R1 is equal to 1 by 2 pi f into R1 Cf, which implies that gain decreases with increase in frequency. The frequency response of the basic integrator circuit is shown in the figure. Let Fp is the frequency at which gain is 1 or I can say 0 decibels. The value of Fb can be calculated by transforming the circuit into the S domain, that is, in the figure showing the circuit of an integrator, Vin and V0 are functions of S, Vin of S and V0 of S respectively, and Cf is replaced by 1 divided by SCF. The gain of the integrator is V0 of S divided by Vn of S is equal to minus Zf of S divided by Z1 of S, where Zf of S is equal to 1 by SCF and Z1 of S is equal to R1 and S is equal to J omega. Thus, V0 of S divided by Vn of S is equal to minus 1 divided by SCF R1, which is also equal to minus 1 divided by J omega Cf R1. The magnitude of the output voltage, that is modulus of V0S by Vns, is equal to 1 divided by square root of omega square Cf square R1 square, which is equal to 1 by 2 pi f Cf R1. Since Fb corresponds to the frequency at which the gain is 0 decibel, therefore at f is equal to Fb, the magnitude of gain should be 1. Thus, 1 by 2 pi Fb Cf R1 is equal to 1 or Fb is equal to 1 divided by 2 pi Cf R1. Let us consider the circuit of a basic integrator when Vn is equal to 0. When there is no input signal means 0 frequency. In that case, capacitor Cf will offer infinite impedance, that is XCF is equal to infinity, and the capacitor will work like an open circuit. The op-amp circuit behaves like an open loop amplifier. So any offset voltage which is present at the inputs or the input current charging capacitor Cf will produce an error voltage at the output of integrator. This limits the use of the above circuit in practical applications. So, in practical integrator, in order to reduce the error voltage at the output, the circuit is modified by adding an extra resistor Rf in parallel to Cf as shown in the figure. Here, Rf limits the gain at low frequencies and minimizes any spurious variations in output signal. Also, in a basic integrator, gain is not constant over any frequency range, leading to instability. The practical integrator circuit overcomes both the problems of stability and low frequency roll-off, that is, rate of decrease in gain at lower frequencies in basic integrator. The frequency response of a practical integrator was shown in figure 10. At low frequencies, impedance offered by capacitor CF, that is XCF, will be very high. So, net impedance of the feedback circuit will be RF parallel to CF, that will be equivalently be RF. So, the circuit will behave like an inverting amplifier with the constant gain equals to minus RF by R1. At higher frequencies, CF offers a low impedance path, that is RF parallel CF equals RF, and the gain decreases with frequency as in a basic integrator. If FA is the frequency up to which gain is constant, or I can say gain limiting frequency, then up to FA the circuit works like inverting amplifier, and for frequencies F lying between FA and FB, the circuit acts like an integrator. For calculation of FB, the circuit of practical integrator is transformed into S domain as discussed earlier in this module. Here, ZF of S is equal to RF parallel 1 by SCF, which equals RF divided by RF CFS plus 1, and Z1 of S is equal to R1. Substituting in equation 20 for gain, we have V0 of S divided by Vin of S is equal to minus RF upon R1 divided by RF CFS plus 1, where RF by R1 is a constant. The break frequency FA at which the gain reduces to 0.707 of its constant value or minus 3 dB can be calculated by equating the denominator to root 2, that is square root of 1 plus RFCF 2 pi FA whole square is equal to square root of 2, which gives FA to be equal to 1 divided by RFCF 2 pi. Generally, the value of FA, in turn R1C1 and R1CF, should be selected in such a way that FA is less than FB. The input signal will be integrated properly if the time period of the T of the signal is larger than or equal to RFCF, that is, T should be greater than equal to RFCF. The ability of an op-amp to integrate a given signal makes it possible to solve differential equations. Integrators are widely used in ramp or sweep generators, in filters, analog computers, signal wave shaping circuits, etc. Let us now discuss the next application of operational amplifier, which is the comparator. A comparator, as the name implies, compares the input signal applied at one of its input to that applied on other input, which is called the reference signal. In this application, op-amp works in the open loop configuration, having two inputs and one output. If the signal on inverting input is greater than that of the non-inverting input, differential input voltage VID will be negative. Therefore, op-amp will go to negative saturation. On the other hand, if the input on the non-inverting terminal is greater than that on the inverting terminal, VID will be positive, resulting in positive saturation. Therefore, any given signal can be compared with reference signal with the help of a comparator. Comparator can be inverting or non-inverting depending on whether the signal to be compared is applied at the inverting or non-inverting. The circuit diagram of a non-inverting comparator is shown in figure. The fixed reference voltage V reference is applied to the inverting terminal. Let us say V reference is equal to 1 volt. The AC signal to be compared is applied to the non-inverting terminal and hence is the name non-inverting comparator. Diodes D1 and D2 are connected to protect the op-amp from damage due to excessive voltage across the differential inputs. In some cases, The op-amps have an inbuilt protection and thus the diodes are not required. Resistor R is connected in order to limit the current through the diodes D1 and D2. When Vin is greater than V reference, the output V0 goes to positive plus V saturated, and when Vin is less than V reference, the output goes to minus V saturated. Thus, the output voltage switches from one saturation level to another whenever Vin is equal to V reference. A comparator converts an analog signal to digital signal. The input and output waveforms for non-inverting comparator with V reference positive and negative are shown in the figure. Inverting comparator works in the similar way with V reference at the non-inverting terminal and input signal at the inverting terminal. The input and output waveforms for inverting comparator are shown in the figure. We can see that for an inverting comparator, when Vin is greater than V reference, the output goes to minus V saturated, and when Vin is less than V reference, the output goes to plus V saturated. We discuss the next application of op-amp, which is the zero crossing detector. A comparator can work as a zero crossing detector provided that V reference is set to 0 volts. Figure shows the circuit of an inverting comparator which is used as zero crossing detector. The corresponding input and output waveforms are also shown. The output shows that the zero crossing detector is basically a sine to square wave converter. Output V0 is driven to negative saturation when the output signal crosses 0 in the positive direction, and it is driven to positive saturation when the input signal crosses 0 in the negative direction. Thus, it may be easily inferred that in which direction does the input signal crosses 0 volts. A non-inverting comparator works as a zero crossing detector in the similar way, except the fact that the input and output waveforms are in the same phase. So students, let us now summarize what we have learned in this module. Operational amplifier as adder or summing amplifier is studied in the inverting and non-inverting configurations. The expression for output was derived. The working of operational amplifier as subtractor was studied. Operational amplifier was studied as differentiator. The practical circuit of differentiator was also discussed, and the frequency response was studied in detail. Operation of integration using an op-amp was explained along with the practical circuit and the frequency response. Finally, the application of op-amp as non-inverting comparator and zero crossing detector was also demonstrated. Thank you students for your attention.